Okay, we are continuing on here, chapter 4, and last time we talked about into the end of chapter 3, some exceptions to the octet rule. And those exceptions are an incomplete octet, which we do come across a little bit. And incomplete octet again means that it has kind of less than 8 electrons around it. Really the one that probably you'll see the most in that range, like we talked about, was boron. That's very commonly kind of the incomplete octet that you see. Again, technically beryllium, aluminum as well can kind of do that, but a lot of times it is going to be boron. There's also the odd number of electrons, and those are obviously much like it implies there. You basically have an unpaired electron in that case. Something like NO that we saw has that situation that occurs. Makes them really, really reactive because of that unpaired electron. The last one that we come across probably the most out of all three of those exceptions is the expanded octet. And the expanded octet is one are elements that can go above 8 electrons. And again, as we talked about there, that is pretty much where sulfur sits on the periodic table, to the left, to the right, and then again down sort of from sulfur. Again, really the non-metals we're talking about there. And that again is because that is where we start to see the d orbitals being available for those guys. So they do have places where they can stash those extra electrons. As we also talked about, obviously before that, above it, where oxygen and all those guys are on the second period, they don't have the ability to do that. So they should never kind of go above that. We also talked about bond energy and bond enthalpy. We could calculate the change in enthalpy for a reaction based on making and breaking bonds in a chemical reaction. And again, when we make bonds, it's an endothermic process, which means that the energy should be positive. When we break bonds, it is a I'm sorry, let me see that backwards there. When we break bonds, it is a endothermic process. Got to put energy in to do that, to get them to basically break apart from one another. When we do make bonds, it is an exothermic process. They kind of have to lose some energy, kind of slow down, if you want to think about it that way, so that they can come together. We could calculate that basically by adding up all the bonds that we broke and all the bonds that we made. And obviously you could do it by just making the appropriate sign on endothermic being positive and negative for our exothermic process there of making bonds, and add them together, and it'll give you an overall delta H value for that reaction. Again, if it's positive overall, the delta H value means overall the reaction is endothermic, going to be absorbing some energy. And if it is a negative value, then overall that's going to basically be releasing the energy. We then moved into chapter 4, which was about geometry, and we talked about 2 different types of geometries. One is the electron pair geometry, which describes how the electrons are arranged around the central atom. The other one is the molecular geometry, which is also sometimes referred to as the shape, and that's really the overall shape of the atom. Now, in certain cases, those names will be the same, and they are the same when you have a basically a Lewis structure where there's no non-bonding electrons on the central atom. And the reason that is because there's no lone pairs or non-bonding electrons on the central atom. Pretty much every electron pair there is a bonding pair which has an atom attached to it. So as those electrons move around the central atom, so does the bonded pairs and the atoms move, which results in really the same shape that's going to develop for the overall shape as the electron pair geometry shape, because as those electrons move. It's only when we start to introduce non-bonding electrons around the central atom that we actually do see a difference in the overall shape of the atom or molecule. And that is because, again, it's lacking those sort of bonded pair, and it also has a little bit more room to move out and spread out. And that's really the whole basis of the geometry idea, is they are all electrons, which means they really don't want to be near each other, but they have to be near each other because they're kind of locked into a bond, but they are negatively charged. So they're going to try to get as much space from one another as possible. And sometimes they're able to do a little bit more spreading out when there's those non-bonding electrons there, because they're not attached to an atom, and they're able to kind of spread out a little bit further from one another. And it's really based on the different types of interactions that you have in terms of electrons. If you have bonding electrons near bonding electrons, then that's sort of the most tolerable situation, to sort of the worst situation where we have non-bonding near non-bonding, and that's sort of the worst situation. And that's where we get really those guys be able to kind of spread out a little bit further from each other than is they could do with those bonds that are present. Any questions on any of that stuff? So again, knowing the electron pair geometry, molecular geometry is something that you do need to know. I put up on Canvas another little handout that makes a table of electron pairs, bonds, and the geometries and bond angles that go with it. And again, as we talked about, memorization is probably the best way to do that and to try to visualize the shapes and all that kind of stuff in your head. Any questions on any of that stuff we talked about? Okay, so we're going to talk about another type of bonding theory next, which is what is known as hybridization. And hybridization is an idea of bonding, and there's a few different types of theories of bonding: valence theory, Lewis theory. We have hybridization, molecular orbital theory of bonding, and all these theories do help explain certain types of properties that we do see with molecules. For example, hybridization also helps explain the geometries that we see and the bond angles that we see with these type of molecules, rather than just looking at the Lewis sort of structure and trying to figure out the geometries that would go with it. So the valence bond theory describes, as we talked about, basically the idea of a covalent bond as a result of overlapping of orbitals in bonded atoms. And obviously in this overlapping region here, this is where we would expect the electrons to be shared between the two nucleuses, and that will make our sort of covalent bond. Now, the idea of hybridization and making hybrid orbitals is, if we think about sort of these orbitals the way they are, you know, you have, say, an s orbital and like a p orbital. They are, in theory, sort of theoretically different shapes. They're also at different energy levels as well. So it makes for some interesting sort of overlap that could occur with these different orbitals, and may not result in sort of the bond angles that we see in these particular molecules. So the theory of hybridization helps us sort of explain these sort of geometries that we do see. And the idea of hybridization is we take these atomic orbitals, and atomic orbitals are like S's and our P's and our D's and our F's. So we take these atomic orbitals, and they basically will hybridize together. They basically will mix and make sort of a hybrid orbital of the two. The result of that is that we will end up with these orbitals that basically have the same shape. They're also going to be in terms of the same energy. So we'll create these orbitals that end up same energy level. They also have the similar shape, and it allows for better sort of overlap of everybody sort of coming together and making those bonds. Now, the total number of hybrid orbitals formed is equal to the number of atomic orbitals hybridized. So, for example, if we have our S, for example, here, and we'd have our P subshell, if we took an S and a P orbital together and hybridize them, we basically took 1 and 2 atomic orbitals. That will result in 2 sp hybrid orbitals that will end up being the same sort of shape. They will also end up being on the same energy level. And because we mix together 2 atomic orbitals, we get out 2 hybridized orbitals, which can be used for bonding. So that is always the case. You mix 3 atomic orbitals, you get 3 hybrid orbitals, and so forth, that will come out. So let's talk about sort of the first type of hybrid orbital, which is the one I just did there. If we take our s orbital, which you can kind of see here is our sphere, and there's our sort of figure 8 happening there of our p orbital. And again, if we mix these together, we're going to create those hybrid orbitals. So we'll have our, again, our s and our p. And we're going to take those guys here and make, in terms of energy, two hybrid orbitals that are equal in energy. This also, as you can see, leaves two p orbitals here that are unhybridized. So these hybrid orbitals will be made, but in this particular case, it will actually leave two of the three p orbitals in that subshell unhybridized. So they'll just be regular sort of p orbitals that will be there. And then remember, this is like px, py, pz. So you have like your py or pz orbitals, which again are just the regular old sort of figure eights, if you will, unhybridized, just like they normally are. A little hard to kind of see here, but when they do come together, to a better color so you can actually see it. When they do come together, they create this sort of hybrid orbital that, you know, sort of looks a little bit like this. And they have sort of the same shape that occurs. Now, hybridization is linked to electron pair geometry. So the electron pair geometry is linked to the hybridization that occurs. So when we think about the electron pair geometry that we talked about, and we think about what happened here, a really simple way to remember it is, in this case, I took 1 and 2, right, orbitals together, right? And two electron pairs is linear, yeah. And that is your 180-degree bond angle that we saw. So SP, basically two letters. You can think of it like two electron pairs. It goes with the electron pair geometry of linear in this particular case, which means they will be 180 degrees spread apart from one another. So if we take an example of this, like beryllium fluoride, and if we look at beryllium, which is number 4 there, a little 1s2, 2s2, it has basically two valence electrons. And if we were to draw sort of our electrons here, our 2s, we would have 2 electrons, and then we would have our 2p orbital. And what typically happens in this case, and again, just to remind you, it looks something like this. And we know just from perhaps looking at the Lewis structure here, this is obviously an incomplete octet. And we know from looking at it that it has 1 electron pair, 2 electron pairs right around the central atom. So we know that it's going to go through sp hybridization basically just from that. What's going to happen is during the hybridization process, a lower electron in the s will gain enough energy and will be promoted up to a higher energy level there into the p, and you'll get that sort of promotion that occurs. And the result of that is we will now have an unpaired electron there, and we'll have an unpaired electron here. It will then go through its hybridization, and it will then create 2 of our sp hybrid orbitals, which each basically have an electron in there. It will also have those unhybridized p orbitals that are there. And now, and by the way, what we're looking at here is the electrons in beryllium. And now really we could account for our bonds that's going to happen. You have your fluorine, for example, which will share an electron here to make a bond. And you also obviously have a fluorine over here that's able to bring those electrons together basically and make the other bond that is present. So the bonding that can happen in this case will be between the sp hybrid orbital in the beryllium and the fluorine orbital as well. Fluorine could go through hybridization as well, but that's basically the bonds that we will see here. Any questions on that there? It's a prettier picture than when I drew, but it's pretty close. The next type of hybridization that occurs is going to be the sp2 hybridization. And the sp2 hybridization, much like the name implies, we're going to take our S, and in this case, we're going to take two p orbitals that are going to come together. So that is a grand total of 3 orbitals that have been hybridized. That is going to result again in 1, 2, and 3 sp2 hybrid orbitals basically being made. We will in this case have one unhybridized p orbital. And again, you can kind of see it here. There is the s orbital, the kind of circle. There is a p orbital coming through here and a p orbital coming through there. So those guys are going to be the ones that are going to go through the hybridization. The result of that is we are going to get 3 of those sp2 hybrid orbitals that occur. We did take our 3 basically orbitals together, which is like 3 electron pairs. So this electron pair geometry for 3 is trigonal planar. So trigonal planar goes with the sp2 hybrid orbitals. And as you can see here, it is what makes the 120 degrees, right? The sort of triangle that we talked about when we're doing geometry, that basically occurs there. So trigonal planar electron pair geometry is associated with sp2 hybridization happening. Again, it creates these 3 sort of equal hybrid orbitals that occur, and will end up being 128 degrees. So if we look at another sort of incomplete octet, BF3, and again, if we sort of draw it through here, that is BF3. And if we look at boron here, and again, this is the electron configuration for boron, which basically is 1s2, 2s2, 2p1. These are the 3 valence electrons that we see in this picture here. Again, the same thing is going to happen. We're going to get this lower electron getting promoted up, and just like normal electron configuration, it will actually end up in the one next to it, right? As those p subshell gets filled 1 electron at a time, and then comes back, right, and pairs up. So when that electron gets promoted, it will do the same sort of filling as normal, and we'll go actually to the one to the next to it. The result of that is we will then get our hybridization that will occur between our s and our 2p orbitals there. And again, going to create 3 sp2 hybrid orbitals on the boron here. Now, each of these basically can go and make a bond with the fluorine. So each of these would then be able to kind of go and make the bond with the fluorine atoms in this particular case. Now, when we look at hybridization, or you want to sort of figure out the hybridization, a lot of times you could start with the Lewis structure and basically sort of figure it out based on sort of how many electron pairs you got going on around the central atom. So that will help you determine what type of hybridization that's going to occur. In this case, we do have our pz orbital here that is unhybridized. And again, that's just a regular sort of p orbital, as obviously our bottom guys have made hybridization. The next type of hybridization that occurs is sp3 hybrid orbitals, or hybridization. And much like the name implies, in this case, we are going to take everybody there. So we're going to take basically the s, and all 3 of those p orbitals are going to make these hybrid orbitals, which again will result in the same sort of shape, also the same energy. Since we're combining 4 atomic orbitals, we will end up with 4 hybrid orbitals, which is sp3 in this particular case. And much like the name implies, sp3, we end up with 4 of these orbitals here. Electron pair geometry for 4 is tetrahedral. So sp3 hybridization goes with our tetrahedral geometry. And that is where we see, maybe hard to see here, but our 109.5 degrees bond angle that we see in tetrahedral that is basically occurring. So an example of this would be like methane. So if we look at methane, and again here we're looking at carbon's electrons, and carbon being 6 there, which is 1s2, 2s2, 2p2. That is the 4 valence electrons that we're looking at here with carbon. And the same sort of process is going to occur through this hybridization process. We're going to get this electron to promote up, and it will end up over here, as that is the next spot where an electron should end up. And then we're going to, as I talked about a second ago, we're going to basically take everybody here, and it's going to go through hybridization, create these orbitals, which are, again, the same energy, the same shape, and allow better overlaps. And in the case here of CH4, it obviously looks something like this. And basically what's going to happen is, which each of those hydrogens, which has a 1s orbital, they will make a bond, basically, right? So, you know, I'll draw it kind of like the picture. Stuff like that. So each of those carbon hybrid orbitals will be able to make a bond with hydrogen, and it would be a bond between basically an sp3 hybrid orbital and carbon, and in this case a 1s orbital there in hydrogen. Hydrogen will not go through hybridization because it only has 1 electron. Everybody else has no sort of the ability to do some of the hybridization thing. Because it only has 1 electron, hydrogen will not go through sort of hybridization. So we get to basically the bonding that will occur here. Any questions on that there? So let's talk a little bit about a couple of things here. Let's actually do this. Let's talk about some different types of bonds that occur. And one type of bond is what is referred to as a sigma bond. And a sigma bond in general results from when orbitals basically overlap with each other, and it's sometimes referred to as head-on overlap. They basically run right into each other, so like straight onto each other. So a sigma bond usually will result from orbitals that will run sort of head-on to each other, so right at each other, and that area where they overlap will result in a sigma bond. You could kind of think of a sigma bond as kind of like the single bond, or the first bond that's made between 2 atoms, is the way you could kind of think about it. So a sigma bond is usually the result of those sort of first bond that occurs, and those orbitals basically just heading basically right at each other, side to side. Bonds in which we have that head-to-head overlap is referred to as sigma bonds. So, you know, any of those ones we just looked at where it made basically like a single bond would be considered a sigma bond. A pi bond, as we'll talk about in a second, is the results that occurs when we have double bonds and triple bonds that happen. Now, when we talk about hybrid orbitals, in the couple examples that we looked at previously, there are all sort of bonding electrons that were basically occupying those hybrid orbitals. They had 1 electron. They're able to basically make a bond. Now, it doesn't necessarily have to be bonding electrons that occupy hybrid orbitals. you can have non-bonding electrons that occupy orbitals, and we see that in NH3, and we also see that in H2O. And we'll take a look at those in just a second. But again, even the hybridization for things that have non-bonding electrons involved can be explained or seen in the hybrid orbitals. As we talked about, again, you result in these sort of stronger bonds. That unhybridized orbitals, you're kind of mixing things that are similar energy, similar sizes, and allows for things to sort of mix together a lot better. So if we look at something like nitrogen here and NH3, and before we do that, actually, let's go back this way here. So what is the easiest way to basically figure out, the hybridization of something? And really the simplest way to do it is, you can think of it like we talked about electrons configuration. There's S's, there's P's, and there also are D's, right, that come next for our expanded octets. And really, we looked at a couple here. We had beryllium chloride, I think, boron chloride. We had CH4. So really, the easiest way to identify what the hybridization of something is going to be is to count the number of electron pairs around the central atom. Now, when you do this, much like what you do when you're doing geometry, we treat double bonds and triple bonds as one electron pair. So when you're doing hybridization, you need to do that as well. So you count those electron pairs the same way as you would be doing it as you were doing geometry. So for example, here, this guy has 1 and 2 electron pairs, as we talked about. So frankly, if you're not sure, you can basically just arrange it like this. You got your 1s orbital, your 3p orbitals, and your d orbitals. And you can basically just count off the numbers, 1 and 2. That's an s and a p orbital. And that's an sp hybridization that central atom is going to basically undergo. We come over here to our BF3, 1, 2, and 3. Do the same thing. Start with the S, 1, 2, and 3. That's an S and 2 Ps. That would mean that the center guy is going to be sp2 hybridization. Here we have 1, 2, 3, 4. Again, just starting at the bottom, 1, 2, 3, and 4. That is an S and 3 Ps, which means the center here is going to be sp3 hybridization. So that's just really a super easy way to pick out the right hybridization. You don't even have to really remember the geometry that goes with it. You basically just need to count the electron pairs, and hopefully you know how many orbitals an S, a P, and a D's have. You just basically start with the S, go to the P, and then obviously we would go to the D if we needed. And if I went to the D, say one of them into the D, that is an S, a 3 Ps, and a D, right? And that would be sp3d hybridization. And 5 electron pairs is basically what that would result from. And that is triangular bipyramidal, those sort of expanded octets that we talked about last time. And maybe even I go one more into the D. That's now an S, that's 3 Ps and 2 Ds. And that is, we just count how many boxes, 1, 2, 3, 4, 5, and 6. That is 6 electron pairs. And that is your octahedral hybridization that would occur. Obviously, this guy would be 5 electron pairs. So we can't even apply hybridization to our expanded octet sort of geometries that we talked about. And honestly, that is probably the easiest way to quickly and easily identify what the hybridization of that atom is. Again, as long as obviously you count the electron pairs correctly. And really the only major thing you have to worry about is double bond, triple bond counts as 1 electron pair. The other thing that sometimes people miss, and we're going to look at it here in just a second, but it doesn't matter the type of electrons that are around that atom. Again, they could be dots, they could be lines, it could be bonding, non-bonding. You would count them again, just like you were doing geometry. It doesn't matter if they're lines or dots. You count them the same way. Any questions on that? So literally you could just mark it off and you'll have the right hybridization and you'll be good in most cases. So let us take a look at some of these ones that where maybe we do have some non-bonding electrons sort of involved. So if we look at something like NH3, and if we drew the Lewis structure for NH3, which I think we did at some point, it will look something like this here. And again, we could really just from the Lewis structure, if we drew a correct Lewis structure, we could apply what the hybridization of this guy should be by doing what I just said. You know, we could just sort of count it off. So in this case, it has 1 electron pair of the nitrogen, 2 electron pairs, 3 electron pairs, and 4 electron pairs basically around the nitrogen. And again, I'm going to start with S here. 1, 2, 3, and 4. So I marked off an S and 3 P's. So that should be sp3 hybridization just should occur there with the nitrogen. First off, any questions on that there? So that's important for us to understand and sort of explain where each of these sort of electrons basically end up and what accounts for them. So to do that, we're going to look at the electron configuration here for nitrogen, which is our central atom. And that's a 1s2, 2s2, 2p3. And basically nitrogen here has 5 valence electrons, right? So if we look at our nitrogen, we have our 2s, our 2p, right? And obviously we should have our electrons like that. And in the P, we should have something that looks like this. So from our Lewis structure, we can predict that the hybridization for the nitrogen should be sp3. So the beginning part of the hybridization process is the same. We're going to take this electron here on the bottom and is going to get promoted up to the P's. At this point, though, we do have an electron in each of the p orbitals, right? Which means this incoming electron should end up over here, like we did with electron configuration. And the result of that is we will end up with this, this, and this. At this point, we know we're going to hybridize pretty much everybody that is there. So we're going to take the S and all of the p orbitals here, they're going to hybridize. And as it goes through its hybridization, and again, this is obviously the nitrogen we are looking at here. We will end up now with 4 equivalent hybrid orbitals that are a little bit lower in energy than some of those guys to begin with, but they're all now at the same energy. And these are all going to be sp3 hybrid orbitals. And again, we will have this situation. And again, this is our nitrogen that is present. All right. Any questions so far? All right, so I'm going to redraw my picture here. Apply some numbers here. So I'm going to call this bond over here bond number 1. I'm going to call this bond here bond number 2. I'm going to call this one bond number 3, and I'm going to call my lone pair number 4 there in terms of electrons that are happening. So if we look at what's going to happen in this case, we will make a bond between, and again, not drawn correctly in terms of energy, but I'm just going to kind of throw it up over here for room's sake. We're going to make one bond between the hydrogen 1s orbital and an sp3 hybrid orbital in nitrogen, and that would count for, say, bond number 1 right there. Yeah. We also would have another hydrogen, right, that has a 1s orbital, and it can make a bond over here, and we'll call that one bond number 2. Actually, maybe we should call that 3, but we'll call it 2. Why not? And lastly here, again, I'm just not drawn correctly in terms of energy, but correctly in terms of space. We will have our 1s orbital here for our hydrogen going to make a bond here to this hydrogen, which would be our 3rd bond. First off, any questions on that? Each of those bonds those are all sigma bonds. So each of those bonds would be a result of the orbitals basically coming head to head and overlapping with each other. So each of these guys here would be sigma bonds. So in this case, there are 3 sigma bonds. Yeah. So the last thing that we need to account for in our Lewis structure and in our sort of hybridization is the unpaired electrons at number 4, right? At spot number 4 there. And that is accounted for right here. So this hybrid orbital, before we kind of made any bonds, paired up right away. And these account for our 4th and our unpaired, or I guess non-bonding electrons is the better way to put that. Our non-bonding electrons are our lone pairs. So even this hybridization model can sort of accurately describe where those non-bonding electrons end up, and also those lone pairs, which are the same thing, also end up. Any questions on that there? Now, let's take a look at another example here, and let's take a look at water. I think there's water. So water, as we hopefully know, looks something like this. The hybridization of water should be what in this case of the oxygen in the middle? What is the hybridization of the oxygen? So let's see. So oxygen, we have 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs, which means 1, 2, 3, and 4. That means that the oxygen here should hybridize as sp3 hybridization in this case. Any questions on that? So again, here you can see it doesn't matter if they're dots, doesn't matter if they're lines. You just want to count them like you normally would as you're doing geometry to figure out the hybridization. And again, you can mark it off over there on the right and figure out your hybridization. So if we look at the oxygen here, which is 8. So oxygen's electron configuration, 1s2, 2s2, 2p4. That is the 6 valence electrons that oxygen has. So if we were to draw our little sort of diagram of where all of our electrons are headed for the oxygen here, we would again have our 2s, we would have our 2p, and it would look something like this to begin with. So at this point, we're going to get that sort of promotion of the lower electron to the higher electron, our energy level. And much like electron configuration, it will then end up over here in the center, right, as it should pair off. And again, we will end up with something like this, and our S. And we know from our Lewis structure that we would expect sp3 hybridization to occur, which means everybody's going for the ride here. And we're going to then, since we put together 4 atomic orbitals, going to result in 1, 2, 3, 4 equivalent sp3 hybrid orbitals. As we could kind of see, we got some that are filled up here. And once again, this is our oxygen all the way through here. At this point, we could kind of visualize what will happen. Again, if we kind of look at our water and we just assign some numbers to everybody so we could follow it, we'll call that 1, 1, that 1, 2, we'll call that 3, and those electrons 4. What's going to happen is we're going to get a bond between the oxygen, I'll just draw them up here for space's sake, between the hydrogen 1s and the sp3 hybrid orbital and oxygen, going to make, say, bond number 1 there. We will also have obviously another hydrogen here. It's going to do the same thing. And that would account for those 2 bonds that we see. Each of these bonds would be sigma bonds that are going to occur here. So those are each sigma bonds. Now, what is left on our picture is basically our lone pairs, number 3 and number 4. And that is accounted for right here in our hybrid orbitals, where they sort of paired up through the hybridization process here. These would account for our lone pairs, our non-bonding electrons that we see on the oxygen in the center atom as well. So again, here, the hybridization process does adequately sort of explain where all the electrons end up, and even those non-bonding electrons that are not part of a bond. Any questions on that there? All right, let's take a look at a couple of other examples and what happens when we get maybe some double bonds involved, or maybe even some triple bonds. So we have something like C2H4, and if I were to draw this, give it the old college drawing here, we'll do a little bit of this action is what it should look like. So in this particular case here, we do have 2 central atoms, right? We have each of the carbons. So we have carbon 1, I'll call it, and we'll call this one carbon 2, just for numbering purposes. Now, as we talked about, when you have multiple sort of central atoms, you could do really the geometry for each one separately. Kind of put your hand over one side, right? And then kind of put your hand over the other side, and you could assign it. So when we're trying to assign hybridization of, say, each of these carbons, we do want to kind of do the same thing, and we could have our little guy here to help us figure out what is the hybridization going on. So if we were to look at carbon number 1 here, it has how many electron pairs around it? It has 1 electron pair, right? 2 electron pairs, and this double bond would count as only 1, right? So just like you're doing geometry, even though it's a double bond for hybridization, it would only count as 1. And that means that if we were to count off our hybridization, we basically have 1, 2, and 3 going on there, which means this first carbon should be sp2 hybridized. And if we look at carbon number 2, what should it end up as? It really should end up as the same, right? It has 1 electron pair, 2 electron pairs, and once again, that double bond would count as only 1. And that also would give us 1, 2, and 3 if you went through there, which means the hybridization of this guy is also sp2 hybridization that's going on. So you can figure out the hybridization just like that. And if it is a question of just what is the hybridization, that's just what all you have to do. You don't have to draw arrows or those type of things, obviously. And we are going to draw sort of the arrows and the electrons here again to basically account for all the bonds and electrons that we see there, and talk about how some of these other bonds form. So in this case, we're going to look at the central atoms, and the central atoms in this case is carbon, which is 1s2, 2s2, 2p2, and carbon being group 4 there, this being the 4 electrons. So each of these carbons will go through hybridization, and before it looks something like this. And it's going to promote that electron up to there, and we're going to hybridize sp2 this time, which means we're only going to take an s and only 2 of those p orbitals in this particular case, right? And when we do that, I'm just going to kind of draw below it. So this will end up with 3 sp2 hybrid orbitals, because we hybridize 3 atomic orbitals. Each of those will have an electron. It also means that we have 1 p orbital that is unhybridized, and that's, by the way, the pz orbital there. We have that 1 pz orbital that is unhybridized, right? Any questions on that so far? So that would be for the carbon, say, on the left, and we'll call it carbon 1. And since the carbon on the right's identical, it pretty much will do the same thing and it will end up in the same spot. So we could really redraw one of these guys here. For the second carbon, it also will end up with an electron in each. It also will end up with a 2pz unhybridized orbital that has an electron, and that would be like carbon number 2 there. All right. So let's take a look and see if we could sort of account for, all the bonds that we got going on in this particular molecule. So let me maybe clean up a little bit of this here. Get rid of that, maybe. Get rid of the entire thing. Okay, so all right, so if we look at all this stuff that's going on, I'm going to call this number 1 there, that bond number 2, this bond number 3, this bond number 4, and we got the double bond in the middle. We'll call this number 5 and number 6. All right, so we're going to try to account for pretty much everything that's going on in this particular molecule and sort of where the electrons sort of come together. All right, let's start with the outside ones first, which is the bonds to the hydrogen. So we'll kind of draw it like it is. So I'll put the hydrogen over here. So we have a hydrogen that's a 1s orbital, and it can make a bond between carbon number 1 there, and that would be a sigma bond that's going to occur there. We also have a similar bond there, right, with another hydrogen that will bond to carbon number 1, and we'll call that bond number 2, which would be our sigma bond. So we've now accounted for basically bond number 1 and number 2, going to be the 1s orbital and the hydrogen bonding to the sp2 hybrid orbital in the carbon. We're going to do the same thing on the other side. The second carbon has a similar sort of arrangement there. It has a hydrogen that's going to make a bond. We'll call that number 3, and that is also going to be a sigma bond. And we have another hydrogen that can make a sigma bond over here for number 4, right? All right, so far we have basically accounted for all the outside bonds, right? So the bonds between the carbons and the hydrogens. What is left is the double bond that's in the middle, right? Between the two carbons that I labeled number 5 and number 6. So the first bond of that double bond, if you want to think about it, is going to result from the two carbons coming together here. And we can see that each of them still has a hybrid orbital available. So that first bond there will result from those two guys coming together, and that would be number 5 on my picture. That also is going to be a sigma bond. So that's going to result in those two hybrid orbitals basically heading right at each other. So clearly we've used up all of our hybrid orbitals, right, to make all of our sort of bonds going up at this point. We still have one more bond to go, which is, if you want to think about the second line for the double bond, right, or the second bond to make that double bond. So the second sort of bond there, which would be number 6 right here, the only thing that is left at this point is the unhybridized p orbitals are going to come together to make sort of the second bond in that double bond. So the first bond in that double bond comes from the two hybrid orbitals of the carbons coming together to sigma overlap. The result of the double bond here actually happens differently than, say, the sigma bond where they come head to head. And that is because what is happening here is we are dealing with unhybridized p orbitals, and unhybridized p orbitals in my artist rendition look like this, right? So each of those carbons have a really badly drawn figure 8 p orbital that's happening. This would be, say, the guy that's on the first carbon. This would be the guy on the second carbon. Now, because these are unhybridized, they're not going to actually come at each other head on like the sigma bond happens. What happens when we have unhybridized p orbitals and they overlap what is referred to as above and below, or sideways overlap is what this is sometimes referred to. And they kind of overlap at those lobes above and below, kind of the plane of the bond. So the bond's kind of in the middle and they kind of overlap. The two balloons on top and bottom kind of come together. And that overlapping area is where the electrons would kind of be shared to make this. This type of sideways overlap that occurs between unhybridized p orbitals are referred to as pi bonds. So this last overlap that occurs here between the unhybridized p orbitals is what is referred to as a pi bond that forms from those guys. So in essence, when you have a double bond, the first part of the double bond is a sigma overlap head to head. The second part is a pi bond that occurs. Any questions on that there? So once again, here our hybridization model does pretty much adequately describe where all the bonds are coming from. Just so you know, again, this is supposed to hopefully help you understand where everything is coming from. You probably will not be asked to draw all the arrows and stuff like that, but you do need to be able to do the hybridization. Any questions on that there? So that's what happens in a double bond. We get some sigma overlap, then we have a pi bond. So sigma and pi together make a double bond. So you kind of think of it as sigma bond is like a single bond. A double bond is made up of a single bond and a second bond, which is a sigma and a pi together. And you could probably imagine here, we'll talk about triple bond. Sigma, pi, and pi is basically what's going to make up a triple bond. So let's take a look at that. And in this case, we'll use our carbon example. If we were to draw this guy, we will end up with a triple bond there in the middle of the two carbons. And again, we could apply our hybridization to each of these carbons. We'll call the guy on the left, again, carbon 1. We'll call the guy on the right, carbon number 2 in this case. Now, when we look at carbon number 1, it has one electron pair there. And once again, the triple bond will only count as 1. So effectively, it has 2 electron pairs, which means 1 and 2, which means the hybridization of this guy is actually sp hybridized. If we look to the guy to the right there, carbon number 2 is pretty much the same deal. It's got the triple bond. It counts as 1 electron pair, and that one counts as 2 electron pairs total. And that also means in this particular case, we will end up with an sp hybridization that's going to occur here. Any questions on how I got there? So we're still dealing with carbon as our central atom. And again, carbon looking like this. We just look at his valence electrons. Once again, we're going to get that promotion of the electron up there. That's going to result in an electron in each of these guys. But in this case, different than the previous example, we can see from our Lewis structure that the hybridization is actually going to be only s and p, which means we're just going to grab one of those p orbitals, right? Not both of them. The result of that is we basically hybridize 2 atomic orbitals. So we will end up with 2 hybrid orbitals, which are sp. They each will have an electron. We will also end up with 2 unhybridized p orbitals, py, pz orbitals. And that would be what the situation is happening there with carbon number 1. In this particular case, carbon number 2 is identical to it. So it will end up the same sort of guy at the end. So I'm just going to redraw that there. And it also will have 2 unhybridized p orbitals. All right, so let's see if we could account for all the situation that we got going on here. Again, if we put some numbers on our picture here for our electron pairs and bonds and all that good stuff. We'll call this guy number 1, number 2. We'll go 3, 4, and 5 through the triple bond there. All right, so we'll start with bond number 1, which is between the carbon and the hydrogen. And that's going to occur, if I left some space, I'll squeeze it in here. We'll take our 1s. Hydrogen is going to make a sigma bond there between the carbon and the hydrogen. The guy on the right-hand side has the similar deal going on. It will make a sigma bond between those two guys as well. So that accounts for our outside bonds, right? What is left now, as we can see, is our triple bond, right? So basically 3 lines, if you want to think about it that way. First line, as you can see, is going to come from the overlap of the 2 sp orbitals, 1 in each of the carbons. And that's going to be the first line of our triple bond, which would be a sigma bond in this case. Now, what is left to make the rest of our triple bond is our unhybridized p orbitals. So you basically have those p orbitals on different 3-dimensional axes here, and my bad drawing. So we'll try it this way and see how I do. So what's going to happen is, in this particular case, we will end up with a overlap that's going to happen between, say, these two guys to make the pi bond and the second line of the triple bond. So we'll just call these guys here those. And the next thing that's going to happen to make our third line is the overlapping of p orbitals here to also make a pi bond that will occur between, say, those two guys there. So in this case, we're going to have actually 2 sets of unhybridized p orbitals that are going to sideways overlap to create the second and third bond that we see in our triple bond that's here. And this would be bond number 4 on our chart there, bond number 5, or whichever way you want to go with it. So basically, in a triple bond, it is made up of a sigma bond and 2 pi bonds. So a triple bond, sigma bond, 2 pi bonds, double bond, sigma bond, and a pi bond, and a single bond, basically a sigma bond, basically just straight up overlap of those guys. Question on that there. Yeah. So again, you don't necessarily draw these arrows, just hopefully it's supposed to visually let you kind of understand where everybody sort of ends up. Any questions on that there? So as I mentioned before, and as we saw in those couple of examples, when we do have those multiple bonds, again, they're going to really result from those unhybridized p orbitals overlapping sideways and giving that pi bond that's going to occur. I talked about this a second ago earlier as well. We can again apply hybridization to our expanded octet. So, you know, we had like SF6, I think, was one of the ones that we did there. And like I said, you could still follow this same deal. And in this case, it has 1, 2, 3, 4, 5, and 6 electron pairs. So 1, 2, 3, 4, 5, and 6. That's an S, 3 Ps, and 2 Ds. So that would be the hybridization for that particular guy. So again, we could do it for our expanded one. I will say some books and stuff, for some reason, write it like the D first. So sometimes you'll see it like DSP3 or something like that, or D2SP3. I personally go this way, but some books kind of put the D in front for a reason that seems odd. Okay. So let's talk a little bit about hybridization here, just to finish out talking about that. So let us say we had something like this. All right, so what I'd like you to do for each carbon and oxygen there, what is the hybridization? And what is the total number of sigma and pi bonds in the molecule? All right, go for it. See what you come up with. Okay, let's take a look. See, we'll start with the hybridization. We'll start on the left there with the carbon. Carbon's got looks like 1, 2, 3, and 4. So 1, 2, 3, and 4. That means that's an S and 3 P's is what that guy should be. Carbon next to it has 1, 2, double bond counts as only 1, so that's 3. So that'd be 1, 2, and 3. So that's S and 2 P's that should occur there. Guy next to it has 1, 2, and 3. Also should be 1, 2, and 3. So that also is going to be sp2. Carbon next to it has 1. Triple bond counts as only 1, which is 2, which means 1 and 2. That's an S and a P that's happening there. Guy next to it has triple bond counts as 1. This guy also counts as 1. That also is going to be an S and a P, 2 letters. Carbon here at the end, 1, 2, double bond counts as only 1. So that is 3. So that is a 1, 2, and 3. So that's going to be an sp2. First off, any questions on any of those hybridizations there? Oxygen, you can apply hybridization to some outside atoms. So if we were to apply hybridization here to the oxygen, oxygen has 1, 2, and 3 electron pairs around it, right? Double bond only counts as 1, and that is going to be an S and 2 P's, which means it would be sp2 hybridization. Any questions on how to apply hybridization there? So quite an easy way to do that. Again, 2 things that people stumble upon: double bonds, triple bonds count as 1, and you do count the dots. Yeah, so if you do have dots, you count them just like you would normally. All right, let's talk about then sigma bonds. So frankly, sigma bonds are just all the single bonds basically, right? So we're gonna try to keep track here. That's 1, that is 2, that is 3, that is 4, that is 5, that is 6, that is 7, that is 8. Sigma bonds are also part of the double and triple bonds, right? So that means that is 9, that is 10, and I'm not sure if I missed that guy. That might be 11 right there if I missed that guy. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And one more over here makes 12. Yeah. So it's got like 12 sigma bonds. If I didn't miss any, I added all the extra lines with my hybridization. It's good I didn't count this. Any questions on that there? Now, pi bonds, right, are basically your double and your triple bonds. Kind of the second line in the double bond, if you want to think about it that way. And obviously the second and third line there in our triple bond. So pi bond, we would have one there, right? We would have one there and another one there. And we would have one there, I think. So that is 4 pi bonds total. Yeah. Any questions on hybridization? Sigma bonds, pi bonds, and those things. All right. So like I said before, you need to obviously be able to identify the hybridization like we just did there, figure out sigma bonds, pi bonds, how many you got going on. And like I said, you probably don't need to draw the arrows and all that kind of stuff that we were doing earlier. Any questions on that? So hybridization is another theory of bonding. There's a third theory of bonding, which is known as molecular orbital theory, and we're not going to talk about that theory of bonding here, so you don't have to worry about it. It is in the chapters, so you don't have to worry about it, though. We're going to skip over it because, well, I don't want to talk about it. It happens. It's personal. It's all right. All right. So the last thing we're going to talk about here is, since I wrote on this, I'm going to erase that. We're going to talk about molecular polarity here. So we touched upon molecular polarity in the previous chapter when we were talking about diatomic molecules. And that means when something is a polar molecule, it will have a dipole moment. So those are for just really polar molecules. And they will have a dipole moment. Dipole moments are represented by the same type of arrow that we use for bond dipoles. Again, that arrow should always point to the more negative side and this more positive side. When we talk about dipole moments, though, the arrow basically is pointing to the more negative side of the molecule, and the other side is pointing to the more positive side of the molecule. And it's, again, very similar to when we talk about bond dipoles, which use the same arrows. Points to the more negative side of the bond and a more positive side on the other side of it. Now, polar molecules will have a dipole moment. Nonpolar molecules will not have a dipole moment. And you can kind of think of nonpolar molecules as kind of being neutral in that sense. But polar molecules definitely will have a positive side of the molecule and a negative side of the molecule. Outside of diatomic molecules, which only have one bond, what we're talking about here is the entire molecule as a whole, taking into account all the bonds that are present, whether or not the entire molecule as a whole is polar or nonpolar. As we talked about, pretty simple for diatomic guys, because again, if that bond is polar, it's going to be a polar molecule. And if that one's nonpolar, it's going to be a nonpolar molecule, again, because there's only one bond in the entire thing. So as we talked about, those are really the simplest ones, and really the only place where really sort of the difference in electronegativity values and bond polarity and molecular polarity really do sort of overlap each other and are the same thing. So again, if you got two of the same, which is a homonuclear, like homogeneous mixture, same elements present, it definitely is going to be a nonpolar molecule because they both have the same electronegativity values, and that's the only bond in there. So, and it doesn't matter if it's a double bond, single bond, or triple bond, but in something like this, this would be nonpolar molecule. Again, because the only bond that is present is nonpolar, which means we would expect pretty equal distribution of the electrons overall in something like O2. And again, really what that's going to do is not create a positive or negative side to that molecule. It's going to, again, just be kind of neutral in that sense. There really is no positive or negative side. Obviously, if we have something like HCl, Cl being more electronegative than hydrogen here, we would have a polar bond. And once again, because that is the only bond and it is polar, this would be a polar molecule, where in this case, the chlorine would be the more negative side of that molecule, and the hydrogen would be the more positive side of that particular molecule. Now, if everything worked that way, it would be great, but unfortunately, everything is not diatomic. So when you do get into things that are 3 or more atoms, you do have to take into account a couple different sort of things to evaluate whether or not a molecule is going to be polar or nonpolar. So let's talk about what we do when we do have more than 3 or more atoms. So when you have 3 or more atoms, you have to look at really 2 things, and that is, are there polar bonds? And obviously, if there are not polar bonds, then probably it's going to be nonpolar, the molecule. And secondly, you need to look at the molecular geometry. Or the shape. So not the electron pair geometry, but the overall molecular geometry or shape of that particular molecule. So for example, let's use the classic example of carbon dioxide here. So if we look at carbon dioxide, first off, is there polar bonds? Is the bond between carbon and oxygen polar or non-polar? We see carbon and oxygen in the same period on the periodic table. Oxygen is further to the right, which means it's more electronegative, which means it should be a polar bond, where the arrows would be heading, let's see, towards the oxygen in this case. So it does have polar bonds. So you may be thinking, well, it has polar bonds, so it probably is a polar molecule. But we do need to look at the geometry here. And this guy has 2 electron pairs. It has 2 bonds. The molecular geometry here is linear in this case, which is basically a straight line. So in this particular case, although it does have polar bonds, because of the geometry in this case, they actually cancel each other out. It's basically a straight line. So, you know, if I took my pen, straight line, this is oxygen pulling this way and then oxygen pulling back the other way. I'm actually pulling really hard on both sides of my pen, and my pen is going nowhere, right? It's kind of like tug of war, right? 2 people pulling opposite of each other. They're going to cancel each other out. So because of the geometry of this particular molecule, it is actually going to be a non-polar molecule. And it's a really good example of, you definitely can have polar bonds in a molecule, but because of the overall geometry of it, they may actually cancel each other out and end up with a non-polar molecule. Let's take a look at water. Another good example. And obviously between hydrogen and oxygen, it is a polar bond heading towards the oxygen here. Now it does have polar bonds. The geometry of water here is 4 electron pairs and 2 bonds. That is your bent or V-shaped, which is why it's usually drawn that way. In this particular case, it's kind of like you have this sort of V situation. You got a guy coming this way, sort of meet at the top. You kind of think if you pull from the top, right, the whole thing's going to kind of move. And it actually does have a overall dipole moment, which heads actually in this direction. Which means that this guy would be a polar molecule. That is because those bond dipole arrows, they are vectors. Think in physics, they have direction and magnitude. I fell asleep. And then I woke up long enough to remember at some point they add to each other, and at other points they cancel each other out. So what's happening in this case is sort of this deal. And they actually add to each other, sort of heading in that way. Nobody wants to do vectors. But basically, if you have vectors that are heading in equal and opposite ways, they cancel each other out. Also, if they're heading like right at each other, kind of like a door, 2 people pushing equally at the door, door's not going to swing open either way, right? It's just going to kind of stay there. So vectors can't cancel each other out. They could add to each other. And that is a result of our polar molecule in this particular case. Any questions on that? Now, clearly, nobody wants to draw, like I said, these vectors and sort of figuring that type of stuff out. So there is sort of a easier way to maybe do it. And there are certain geometries which are symmetrical geometries. And those are, for you guys, trigonal planar, tetrahedral. And again, these are molecular geometries. We're talking about the shape, triangular, bipyramidal, and octahedral. What does all these guys sort of have in common? If you draw these guys, and this is the molecular geometry, there are no lone pairs on the central atom. Basically no dots on the central atom. And if you have that situation and everything on the outside is the same, it will most likely be a nonpolar molecule. So for example, if we do this, I want to draw all the electrons. So if we have something like this, is a polar bond heading towards the fluorine, right? Which is more electronegative. And the geometry here is tetrahedral. I do not see any dots on the central atom. Everything on the outside is the same. They basically are going to be all equal and opposites of each other. They're going to cancel each other out. And this guy would be a nonpolar molecule because of that. Now, yeah. Yeah, well, it would not necessarily, we'll talk about linear at the end here, but you have to think about linear for something else. In this case, if we swapped out one of those fluorines, say for a hydrogen, we now have polar bonds heading in these directions. And the carbon-hydrogen bond is pretty much nonpolar, slightly heading towards carbon. That means that we basically have three things pulling this way, right? And nobody kind of pulling the other way. And you could kind of think about it like a rope. It would probably move, and it would actually go from being non-polar in the case of the right to being a polar molecule. So if you have any of those symmetrical geometries and everything on the outside is the same, no dots, pretty much going to be a nonpolar molecule. If you have any of those symmetrical geometries and everybody on the outside is not the same, probably going to be a polar molecule because you're going to get some of that unequal sort of pulling. Any questions on that? That means that there also is some unsymmetrical geometries, which is pretty much everybody else. So in your case, that would be angular, bent, or V-shaped, trigonal pyramid, T-shaped, seesaw, square pyramid, pyramidal. I think that's most of them. So what basically these guys have in common is that if you draw the Lewis structure, the central atom has lone pairs or dots. Right? So if you draw your Lewis structure, these guys will have dots on them, which means they have lone pairs. And if you have that situation and everything on the outside is the same, it will be a polar molecule. Like what we just saw there, water. I see dots, I see everything on the outside is the same, gonna be polar. This guy should be polar as well. I see dots, everything on the outside is the same, unsymmetrical. That would be polar, you know, so anywhere where you have dots, everything on the outside is the same, most likely going to be a polar molecule. Now, there is a couple things that you do need to watch out for to finish this up on. And that is, there are actually two geometries that are symmetrical geometries that have dots. And those two are not those two are, if we were to add them sort of to our list, is linear, and it's not linear of two electron pairs and two bonds. It is linear, that is the expanded octet. And that is the linear that looks something like this, you know, where it's got like the dots. That linear right there, the 5 and 2 linear guy in the expanded octet. And that's because these guys are pretty symmetrical, the non-bonding electrons. And obviously we end up with basically a straight line. So that usually will end up in a non-polar situation, as they will cancel each other out if they are the same in that situation. And our expanded octet, which is our square planar, which is our expanded octet as well. And that is the guy that ends up basically, that makes the, then we have the 2 dots kind of coming through here, makes that square basically. And because it's a square, basically they will cancel each other out as well because they're equal and opposite each other. So those are the 2 exceptions that can have dots. And if everything on the outside is the same, it will be non-polar because of their really symmetrical sort of geometries. And again, that's a really sort of easy way to do it. Now, the other question, which I think was the question about linear, the 2 electron pairs, 2 bonds, you do have to look at that. In the case of something like what we had with carbon dioxide, where they were sort of heading in the opposite directions, they do cancel each other out. If they happen to head in the same direction, they would cancel each other out. But it is possible in a linear situation that they could perhaps head in the same direction, right? Which would mean that they would be polar because everybody would be going in the same direction, like one person pulling on the rope by themselves, and they would kind of go that way. So that one's pretty simple to sort of figure out because it is linear. So if they're heading in the same direction, it could be polar. Opposite directions, it will be non-polar. Heading right at each other, it would be non-polar. So that's the only one that you sort of has to remember. And I would say that's probably the quickest and best way to figure those things out when you are looking at polarity. Any questions on that there? All right, we're pretty much done with this chapter. We'll